from the website. We have what we have is capacitor. Capacitor is actually a device which we can use to store energy. So we must be able to charge it. Able to charge it first. So the symbol of capacitor looks like what you saw in the PowerPoint. Let me show you the PowerPoint. I'm always in the wrong place. Okay. So this is how a capacitor looks like in a way. They have two plates, one plate, another plate. The top plate is being connected to a positive terminal. The bottom plate is connected to a negative terminal. So what happens is the top plate will store positive charges and the bottom plate will store negative charges. Even though I'm trying to say the word stores charges, what I meant here is the net charge on the top plate is positive and the net charge on the bottom plate is all negative. But the total charge remains the same. The total charge remains the same. Positive 4, negative 4, something like that. Okay. So a capacitor is actually a device that stores electrical charge or energy. Can you just say the word energy first? Then I'll explain to you how it stores a charge. Okay. So the ability to store charge is measured as its capacitance. Capacitance is a property. Larger capacitance means it can store more energy. Okay, a charged sphere is an isolated conductor that has capacitance. I mean, we were discussing about charged spheres yesterday and a few other classes. So if you can charge a sphere, then it has a capacitance as well. Okay, same goes to here. A pair of plates, parallel plates, they can have positive and negative charge, and therefore they have a capacitance. So let me explain by some very simple diagrams. The symbol of capacitor is very easy. It's just to draw two parallel lines. So this is quite a complex thing. I don't know whether you can follow the entire thing or not. I will show you one by one. Okay. Charging a capacitor, you need a battery. Don't follow anything first. Don't follow arrows, nothing. Don't follow. The battery, positive and negative. Connect to one plate and the other one connect to the negative plate. We imagine now they have positive and negative charges. It's just imagination, Okay, so when you connect the positive to the top plate will be charged positively, as you can see. The bottom plate will be charged negatively. When that happens, it establishes an electric field from the positive to the negative plate. But the question is now how the charging occurs. I don't know how to stop this, but I will do it now. Okay. So this is the symbol of capacitor, one like this, symbol of resistor, and a battery. So when the switch is open, I can't hold this actually. I don't know how to make it stop running. When the switch is open, we wait for the switch to open. Okay, when the switch is open, look at this. They have equal number of positive and negative charges. When the switch is closed, the negative charges will flow to the positive terminal. Again, when the switch is closed, the negative charges flow from the top plate to the positive. And the positive charges will flow to the negative terminal. One negative charge flow to the positive terminal. One positive charge flow to the negative terminal. Is 1 to 1. If two negative charges flow here, then two positive charges will flow over here as well. We just have a look again, and I will show you some other, maybe this one. Oh, this is a bit different. The red color is the negative charges. This is another way of trying to explain. They are trying to say initially, the plate has same number of positive and negative charges, same number. The negative charges flow and go to the battery, and the battery, what does it do? It pushes the negative charges here. One way of imagining. But the positive charges, which is the positive charges, will flow here. That one is missing. I don't know why this is missing here. It's missing over here. So we go out from here. This is what I saw. See, one negative charge coming from the top plate coming down. Okay, now we just follow this. We see what happened to the positive charges. Keep coming. So the battery is doing work for us. We need a resistor to connect in series. If we don't have the resistor, then what happens? The charging becomes so fast until we cannot see the change in the graph. This T stands for time, not temperature. Q for the charge. Every time one negative charge leaves, we go and occupy a space over here. So what happens is now this becomes neutral. This one also becomes neutral. This one also becomes neutral. So this will come and go here. And then one more, last one. Come on, move faster. You see that, huh? It is moving slower and slower. They have done it so well. Why is it moving slower and slower? Because the accumulation of charges here is becoming more and more negative. So it's finding more difficult to go here. The speed of the electron, initially it was very fast. Now it's slow. As the bottom plate is becoming more and more negative, it's finding it more difficult. There's a repulsive force done. Okay, I'll stop here first. I'll stop here. Hold on. Stop first. This is a repeated lah, huh? Repeated. I'll go back here. Okay. Oh, all right. Oh. Okay, done. So what happened? We have 1, 2, 3, 4 positive charges, and you calculate 1, 2, 3, 4, 5 negative charges. So what happened to all these? This one becomes a neutral. This is another way of trying to imagine. Another way of trying to imagine how this is being the charging process occurs. What moves in a capacitor? What is moving is only the electrons. Yes, I do agree. But why we have positive? Because technically there's a lot of positive and negative charges, but the battery is only moving the negative charges. Initially, as you saw, this is a neutral. Okay, this is neutral. 1 plus, 1 minus, 1 plus, 1 minus. 1 plus, the minus is here, huh? Plus and minus. So there's no net charge here. Same goes to here, there's no net charge. So the net charge on the top plate and the net charge on the bottom plate are 0. So therefore there is no any potential difference. So the capacitor is not charged. It doesn't store any energy. When we switch on, then the electrons from the top plate move to the negative plate, and then it come here. You can also imagine, if you want, the positive charges, which is the bottom plate, travels this way. There are many ways of trying to understand how a capacitor is being charged. And this is just one example. Some people do this, as what you just saw. They only move the positive charge, negative charges, and they neutralize it with the positive charges. Some people will say, why not we imagine like this, the negative charges go like this, and the positive charges are moving this way, as what you saw earlier, and then that's how it works. Okay, so I go out from here. This person over here they imagine that both charges are moving. It's not wrong as well. So what are they trying to imagine now? The positive charges, the negative charges are moving like this, and the positive charges from here is moving like this. That's the reason why this plate become all positive and this one become all negative. Another way of trying to understand. You get the understanding first, then we will. This is a charged capacitor. The electrons are moving here, and this becomes all negative. The electron from here is going out from here, so therefore this one will become all positive. What is actually moving is only the electron. So what you can imagine now, the electron from here is taken from this particular on the plate on the right hand side by the battery, and the battery will charge it and put it over here. And as you saw in the earlier one over here, basically initially the charges start to leave at a higher speed, but as the time taken for it is short, but as it's becoming more and more negative, the time is taking longer. It's taking longer because it's a strong repulsive force. Okay, let's see what this guy imagined here. Oh, this is not this is just ideas huh? Okay, no problem huh? So when you have a positive here and this is connected to the negative, so what happens is now this plate will become all positive, these are all negative. The sequence has been already explained how does it works. When this happens, only then energy is stored because an electric field is created between these two plates. I don't know what is this, but it's not moving. Oh, this is from the fat thing, huh? I can go into the fat later and explain to you how it works. Yeah, okay, why don't we go into our capacitor CC, yeah, the capacitor lab. We go to here, we go to the basic one first. Okay, capacitance, okay. Battery, 0 volt, 1.5 and negative 1.5, okay. So the separation is 6, plate area also it makes a difference. Okay, what we do is now, I try to on this and make it into 1.5. The more in a 0, no charge. When I make it into 1.5, look at that, this plate become positive, this plate become negative. So if I show the electric field is from the positive plate to the negative plate. So remove the electric, okay? Okay, we can actually connect a voltmeter. Okay, bring a voltmeter, connect, and then I connect here, and I bring it to this plate. It shows 1.4. Why is it 1.4? Because I haven't pushed up. Okay, if I push it all the way up, it shows 1.5. You okay? You understand what happens here? So if I move it down, then what happens is now? It reverses because this is 0, 1.5, and negative 1.5. Huh? It is just changing the pole. Can you see that this is a positive now? When I move it here, yeah, we are just trying to imagine now what the website, what is it trying to say to us now? Let me check and see. Negative, it technically will show negative 1.5 because I'm putting at 1.5. 5. So this one is now negatively charged and this one is positively charged. But I don't want to confuse you today. We just stick to this. Now, if I remove this connection, then the charges technically should stay there. They won't flow. Because why it is not flowing? Because they can't flow between the, throw away this. Like the charges cannot flow between the plates. The reason because between the plates are a space. It's a space. This space is filled with, what do you call that? Maybe it's filled with air or vacuum, or in some cases they use a, what do you call that? In some cases they use it as a dielectric material. It's an insulator, dielectric material. Okay, take out a bulb. Bulb. Okay. Now I have a bulb here. I charge it first, then I connect to the bulb. It will light up until all the charges are gone. No more. I repeat again. Let's light it up. Charge it first, bring it here, and then I touch the bulb. The intensity of bulb reduces. Okay, not only that, I can also measure the voltage. Stay there. I can also measure the voltage and show you how the voltage varies. I charge it first, and then bring it to the bulb and look at the voltage. It's 1.3 and drops to 0. The drop is drastic initially, drop in the voltage, but later it drops slower. Same goes to charge as well. The charge will be higher and then goes lower. So this is just a very simple, this is a very simple idea. So let's try to look for the one which is a bit more advanced. Does your handphone battery uses capacitor? No. Handphone batteries doesn't use, what do you call that? Capacitors. Your handphone battery, your laptop battery, they don't use capacitors. They use lithium-ion batteries. They are real batteries. They are chemically, batteries. They're chemical batteries. These are not chemical. This is just by using electric field. So why we are learning this? Because we use capacitors not to store energy and light up something. It actually stores energy to show in smoothing. Have you heard about smoothing circuit? Smoothing circuit means we're changing AC to DC. So we need a capacitor to smooth the graph. So we use a capacitor. It's like a small reservoir of energy, electrical energy, small reservoir electrical energy. Yeah. Okay, same goes to here. Dielectric. Multiple capacitors, okay, whatever. Okay, let me try to just do the introduction first. So the top plate is charged 1.5. Oh, no need, I don't have anything. Electric field lines, yeah. Electric field lines is like this, I don't want anything. Let's go for dielectric. What's the meaning of dielectric? Dielectric is just an insulator. Okay, insulator. The insulator will prevent the charges moving between them. And we don't really discuss much about dielectric, so I don't want to show you on dielectric much. So if I make it, the top plate is positive, the dielectric itself has charges inside, but they don't allow the charges to move between the plates. They are actually behaving as an insulator. But when we create a positive charge on the top plate, what happens is now the charge on the dielectric, dielectric itself is just a kind of offset. It's just like they have positive and negative charges in the same place. You can't see the negative charges, but they're there. When we bring it inside, the negative charges will be attracted up and the positive charges goes down. It's same like ultrasound. Remember the ultrasound, how we cause it to. So it is just to show you that they don't conduct electric current between them. Okay. So the dielectric, in a way, it increases the concentration of the charge, helps to concentrate. This is air. When we put a dielectric, then the capacitance will increase. Everything else remains the same. Huh? Okay. Okay. We take out this. We take out this. I never worked with this multiple capacitors yet. I don't know what is this. How does it look? Oh, okay. The separation between the capacitors makes sense. Yeah, there's a difference, but it's not the syllabus, so I don't want to talk so much on all this. Huh? Okay, let's go back to our capacitors. Where's our capacitors? Here. Okay, I make it a bit bigger so that you can have a look at it. Okay. Capacitor is a device that I say stores energy. That's the way to say, or charge. And we use a capacitance as a quantity to measure how much charge it can store. Larger capacitance mean it can store more energy. So capacitance is defined as Q over V. Okay. So hold on. Next one is I want to see whether I have the graph or not. No, I don't have it here. It's okay. I will write in my paper. I'll post it to you. We'll discuss from my WhatsApp. Give me a minute, huh? I'll come back to you. Medicine. Not this, not this. Block 3. Okay. There's any way I can rotate this diamond. Hold on. I can't rotate this. Okay, yeah, so it has been already rotated. So can you draw this graph, Q on the y-axis, V on the x-axis, and you draw a straight line. The variation between Q and V is directly proportional. And then you draw a gradient, a triangle here to show that I'm calculating the capacitance. The capacitance, the gradient from the graph, is equivalent to delta Q over delta V. And the unit for it is coulomb per volt, or F-A-R-A-D, farad, small capital F, Michael Faraday, farad. Okay, can you do this first? Yeah.
So farad and Faraday are two different units, is it?
Yes. No, Faraday is just name of person, Michael Faraday. They use his name to come up with this unit, farad. You cannot write Faraday, farad, and that's it.
Okay.
But in capacitance, we don't even use farad, microfarad most of the time, because the charges are very small, microcoulombs or microfarad, microfarad. Okay, done, huh? You're done with the graph. I have no choice. I don't have it in my PowerPoint, so. So whenever you do this, you keep on drawing straight lines. If you have a graph with a larger gradient, then they have a more capacitance. You can directly calculate that. Very simple ideas, delta Q. Now, you always try to show the examiner that you are calculating from the, what do you call, gradient, not a point. Because delta Q over delta V, is just going to be a straight line, yes, I know, but you still do like what I did over here. So, therefore, yeah, that's the reason why the capacitance is defined as C equals to Q over V from the graph that I say is measured in farad, F-A-R-A-D, capital F. What is Q? Charge. What is V? Potential difference on its surface. And you don't have to write this, so no worry. This is not necessary because this is not an part of your syllabus. It's a requirement, but they will show you in the question itself, so you're going to use it on it. And label the plates as positive and negative plates. The Q is actually the charge on either plate, not total charge. Whenever we say that, it's a Q on either plate only. And because if there are 4 plus means there must be a 4 minus. And the V is the potential difference across the plate. Okay, can I move on? Next one. There are many types of capacitors. Well, I tell you, none of this is important for you, but I will just go through none of these. Capacitors can be made of ceramic, polyester, electrolytic. Mylar is actually M-Y-L-A-R. It's a type of polyether film made from stretched polyethylene. I don't know how to pronounce this. And is used for its high tensile strength like chemical. So they use this to make capacitors. This is quite a common one, huh? Ask Mr. Vicky. They look like this. Shiny. It's a mixture of all these things, huh? Oh, what is this? This is a chemical composition, I think. But I don't want to do all these things. Wait, come on, how to go out for me? Back. Okay, got it. So, no. Come on. Yeah. So you know something called Mylar, huh? I don't know how to pronounce it as well. Okay, what is the meaning of dielectric material? Di means two. Okay. A non-conducting material between the plates of a capacitor. A dielectric material always increases the capacitance of a capacitor. Use the diagram below for an explanation. Okay. So, like example, no dielectric. When there's no dielectric, that means air. The capacitance, let's say, is equivalent to C naught. If we put a material, then the magnitude of the capacitance increases more than C naught. Then let's say this is a dielectric. Okay. When we put a polar means like they have one thing, they have plus and minus together. Then the magnitude of the dielectric increases further. C2 becomes more than C1. Don't worry about this. This is just to show you some extra things for you. Even this is not really in the syllabus. Dielectric constant is not the syllabus. What is important will be mentioned by me. Okay. How to charge a capacitor, I already talked to you about, but how to discharge a capacitor? I haven't do that yet. Okay, it's not in the PowerPoint, but I will work on the how to discharge a capacitor using, I'm not sure that I can get anything reasonably good to explain to you. Whatever you see is all discharging a capacitors, like this one here, okay? We just connect a capacitor, a charged capacitor. Hey, no, this is not discharging, sorry. This is charging, this one. When you discharge a capacitor, how you want to differentiate? The capacitor should not have a power supply. They must have only a resistor. So what's happening here is the negative charges that once has been charged now will move back to its home. Go back to the home again. Because why? It's going on its own because there is a potential difference being created between the two plates. So minus. Go up. Same goes to, right? It take the time will be faster initially for discharging, and then it becomes slower and slower. You see, I want to draw a few more graphs. Are you all allowed to come back to college next week? No, you don't have idea? Any email from the college so far?
The information given the verse is like kind of vague. So like there isn't really a clear message as to how we should proceed with everything.
Coming back. Okay. So I think maybe tomorrow we will know, Maybe hopefully by tomorrow. But because the email sent to the teachers, There was, I says that we will have a face-to-face on Monday.
Because the SC sent out a meeting minute yesterday, say something about if students are not comfortable going to class, they may do online classes. We're not really sure like what they're gonna implement.
Yeah. But if you guys are all coming down there, then I'm happy to be there because after all, we have to just take care of ourselves. This thing is not going to over. This is going to be repeated. There will be another, the cases will go down, and then after a few months it will go up again. And due to some, problems, some people are a bit more not responsible in the way they do things. So we have to live with this. I'm sending pictures to you now. Have a look at it. Oh, nice. Okay, so the process of how it is done won't be questioned. They won't question you on that. Okay, let's go back. Are you clear? When you are charging a capacitor, you have to be able to draw these three different graphs. I've already done for you. Your work is just copy and paste. When we are charging, initially, look at the time. The gradient is... Okay, we look into the YouTube later. Where am I now? We have to go back to my WhatsApp. Okay. When we are charging a capacitor, look at the gradient. Initially, the gradient is large, and then the gradient is getting smaller. Why the gradient is getting smaller? Because initially, the charging is so fast, and then it takes a longer time to charge as the plate is becoming more and more negative or becoming more and more positive. So as it's becoming more and more negative, it's more difficult for the electrons to occupy the space. It's more difficult for the electrons to enter the particular plate. So this charging process, the gradient will become lesser and lesser, and eventually at one point it becomes zero. It will become zero, like what I did show here, V against T. Initially the voltage is zero, and then there's a quick, a rapid increase in the voltage, and then the increase in the voltage is getting lesser and eventually becomes constant. Okay, the gradient become constant. Same goes to here. Can you draw a constant gradient? Why the gradient become constant? This is where the charging will stop. The charging stops here. The charging will stop when the potential difference across the capacitor and across the EMF is the same. I repeat again. Charging will stop when the potential difference across the capacitor and across the EMF battery, is the same. So you draw like this. And the nature of the graph is almost the same. When the Q increases, V increases. When the increase is getting smaller, the increase in V also getting smaller. So when you can, how about IT graph? IT you can draw like this. Current is very large. Current is a rate of flow of electric charge. Can you look at the gradient? Very large gradient. So I draw here. And then the gradient is getting smaller and smaller. And the gradient here is zero. So I did draw over here. Do you have any issues from this part here? No, Okay, next one. For discharging a capacitor, when we are discharging a capacitor, we just connect the capacitor to a resistor and the charges will start to flow. Now, the same goes to here. It's not so clear, this diagram. The Q will drop and the V will drop. The Q here means the Q on a plate, okay, the charge. So it's becoming less positive or becoming less negative over time, and eventually zero. Same goes to voltage, will drop and becomes zero. The potential difference between the two plates becomes zero. And the current you must draw here. Why am I drawing the current here, not in the positive region? Because now the current is now flowing in the opposite direction. Earlier the electron was going into the plate, now the electron is going out of the plate. So you still start with a very high value for current, because look at the gradient. The gradient is large, but negative gradient, so I draw here. So you have 6 graphs now. 3, and earlier I give you 1 altogether, 7 ground. Any problems so far, guys?
No, sir.
No, okay. So I explained to you about how to charge a capacitor, how to discharge a capacitor, what is a capacitor about, and a few graphs today. Now tomorrow I'll explain to you arrangement of capacitors in series and in parallel. Okay. And then the other one is today is only 8. The last day for me to enter the marks for tracking is only the 20th. So you don't expect me to enter now because I am not back to college. Once I'm back to college, I will print it out and then I will mark it on the papers, the answers, so that you can get the copy back. And then only then I will add up. Some department, they are doing 3 tracking, but physics only did 2. That's all. No more 3. We're only doing 2. That's it. So I know that I will go through your marks again. If your marks are pretty low, then I will call you individually and give you another test so that you can actually improve your marks a bit more. Okay? Clear? Because from now on, we have to be very careful with all the trackings that we do. I don't want to end up like last year where they started to ask teachers to give me a tracking marks and give your marks for this, marks for that. And then when I saw some of your marks, it was pretty low, and which doesn't reflect your actual, capability. You're much more capable, but on the test you didn't do well. So we will evidence. So that's the reason why I agree. Then you do the work and keep it as an evidence. Every time you do, keep an evidence. In case if I have some issues to back you up, then I'll ask, okay, so and so, please give me the work that you have done some time ago on this paper, on this page. You have to give it to me. You have to print it out, give it to me. Then I'll quickly try to mark, and then there will be some sort of evidence to help you out in your prediction later, Okay. So what we do now? Hold on. Let's go back to Teams. Where are we now? Teams. Where is my Teams? I always get lost in Teams. I can't see my Teams out here. Okay. Teams. Voila. Hey, you don't see me. I can't see you. Where is it? Amida.
No, sir. Just press join again.
Oh, yes, sir. I'm out, is it?
It's actually open 2 windows for you for the Teams.
Oh, okay. I mean, I have to press join again or?
No.
Oh, sorry. I'm back. Can you hear me?
Yeah.
Now I know what happened. Okay. So what I do, I see you tomorrow, okay?
All right.
Bye.
Thank you, sir.
Bye. Yeah, see you. Yeah.
Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Okay, thank you. All right.